I want to show you that a positive integer possessing a particular property cannot be written as the difference of two squares. And so let me write this as not equal to a squared minus b squared, where a and b are integers. Okay. Now you guys may or may not have seen this notation. This means 2 divides n exactly. Let me give you an example. 2 exactly divides 26. And that's because 26 is just equal to 2 times, what, 13? So there's no more 2's in this factorization other than this 2. There's no higher power of 2. Now, let's look at another example to clarify the point here. And y'all, I'm going to use the standard universal negation thing here where you draw your little slash like that. 2 does not divide, let's make up something here, let's say 120. Now, it's clear that 2 is a divisor of 120, but 120 is equal to 2 cubed times 15, right? So it turns out to be a fairly important concept because integers with this property I'm going to show you can't be written as the difference of 2 squares. And there's another way to write this that's slightly more common, folks, and I may try to remember to mention that, but this is the same thing as saying n is congruent to 2 mod 4, actually. It's equivalent to that. That could be a video. It's an easy proof, but this means that n is congruent to 2 modulo 4, not modulo 2. Okay. Now, an important observation, I won't try to prove it. If 2 divides an integer exactly, okay, or fully, I think I've seen it in some textbooks, that implies n is the product of an even and an odd integer for all possible 2 integer factorizations, just 2 integers, okay? So, for example, the one we just did, I think this is pretty clear, okay? Don't make me prove that, okay? Because it means that 2 would have to go with one of the factors, right? And that the other factor would necessarily be odd, right? 2 is the only even divisor. So 2 would have to pair up with one of the factors to give you an even number, and everything that's left has to be odd, right? So that's the reason. That's just the wave your hands proof of this statement, okay? Now, we only have to consider this case. Since 2 does divide n exactly, this is just a restatement of this lemma, if you want to call it that. And if you try to set it equal to the difference of 2 squares, look what happens here. Okay, a squared minus b squared factors this way. All right, and so when you equate the factor pairs, that is when you set 2k1 equal to a plus b and 2k plus 2k sub 2 plus 1 equals to a minus b, and add them together, you see how the b's will cancel out? The b's will cancel out, but you'll be left with 2a. Okay, you'll be left with 2a. And so what we have right here is a manifest even number. But now all of a sudden it's equal to an odd number, right? So this is certainly impossible. Okay, this is certainly impossible. And that means that any number that's this way cannot be written as the difference of 2 squares. So we've proved it. Now you may want to see a concrete example. Let's consider 32. Fully divides 30, right? 30 is equal to what? 2 times 3 times 5. So you see, this makes it real clear that all the possible factorizations, you could have 6 times 5, right? What else could you have? You could have 3 times 10, but notice you're always getting an even factor and an odd factor. All right, what else? Are there others? 1 and 30, I guess. There's going to be 3 divisor pairs, right? So you see, if you try to set a plus b and I'll just pick one of them because the logic holds for the other one too. If you just say a plus b times a minus b equals to 6 times 5, well, you can see what's going to happen right here. If you set a plus b equal to 6 and a minus b equal to 5, what do you end up with? You end up with 2a equals to 11, right? Again, I hope that I'm not showing every last step here, but you equate a plus b with 6 or 5, it makes no difference, and a minus b with the other one, right? And when you sum those up, the b's necessarily cancel, then you're adding 6 and 5. So you see this is equal to 11. This would imply that a is equal to 11 halves. Okay, and again, that's not an integer factorization. So you can see the problem with this. So it's kind of cool. I like this quite a bit. And y'all, by the way, this guy here is the one that I tried to prove this under the premise. This gentleman here, Comets, I guess. I did it by working from this form here, incongruent to 2 modulo 4. And if you check, these two things are absolutely equivalent. This can happen if and only if this can happen. And I had a very unsound argument where I just said that one of the factors had to be 2, which is completely wrong. And this guy very persistently and politely and professionally showed me the error of my ways. So this hopefully is something, a proof more to this gentleman's liking. But again, this and this are equivalent. This is how you see it in a lot of number theory books, that if n is congruent to 0, 1, or 3, you can always write it as the difference of 2 squares. So this is kind of an if and only if. You can check it out for n equals 0, 1, or 3 mod 4. Those type of n can be written as the difference of 2 squares. All right, it's just this particular case. And it took me a while to notice that these two things are equivalent, this notion of divides exactly. Okay, divides exactly as compared to just the single vertical bar, which just says it divides it and you don't know how many factors do divide it. But it's an important concept in number theory, and it's important enough to devote this symbol to it. And I think it comes into play in the Mobius stuff, the Mobius function stuff. But anyway, thanks again to Comet Z.